Okay, 3.13, I would say is a pretty mathematically complicated problem, and the main reason for that is because once again, you're sort of doing that illegal maneuver of sort of equating a Dirac delta to an infinite integral through the use of a Fourier transform. And as we said in problem 3.12, that's not strictly mathematically allowed. You have to be very careful when you do that, because sort of if you just use it willy-nilly, you might end up adding on some unintended constraint that makes your system physically not realizable. That being said, let's sort of get into this problem first and see where it takes us. So 3.13 is asking us to show that we can represent the expectation value of x, which traditionally in position space is the integral of psi star times whatever the x operator is multiplied by psi times dx, and show that we can transform that into momentum space and turn it into something in terms of phi star and phi instead. And what we're going to note here is that apparently in momentum space, the x the x operator, instead of just being x like it is in position space, transforms into something that sort of looks like an analog for the operator in momentum space instead, I h bar d by dp, right? So in order to do this, we're given two hints. Hint number one, where's my pen? Oh, there it is. Hint number one tells us to note that we can equate x times e to the ipx over h bar as this expression instead, negative I h bar d by dp e to the ipx over h bar. So if you solve this out fully, you'll find that, yeah, this is true. And then our second hint is to use equation 2.147, which is the Dirac delta equivalent of an infinite complex exponential integral. So let's start with just the expectation value in position space. So we already know, because we've done this hundreds of times, right, that the expectation value of x in x space is just the integral from negative infinity to infinity of psi star multiplied by x multiplied by psi closed by dx, right? So if we want to convert this into momentum space, the first thing we're going to do is we're going to use Plancherel's theorem and Fourier transform our integrals. So we know that Plancherel's theorem tells us that psi of x comma t can be converted into phi via the following formula: 1 over square root of 2 pi h bar multiplied by the integral from negative infinity to positive infinity of e to the power of ipx divided by h bar multiplied by phi of p comma t times dp. So if we use this sort of transformation, then our expectation value of x is going to turn into something significantly more complicated. Let's pull out the 1 over root 2 pi h bars, and that just turns into 1 over 2 pi h bar. And we have an integral from negative infinity to infinity of our first integral, negative infinity to infinity of e to the power of ipx divided by h bar multiplied by phi of p comma t dp. And remember, this whole thing is going to be complex conjugated, and then we have our x in the middle, and then we have our standard one for the other one, and another integral from negative infinity to infinity of e to the power of ipx divided by h bar times phi of x, or sorry, not x, p, comma t. I'm going to close this with dp, like that. And then I close this whole thing out with dx. And next, I'm going to take advantage of the hint that I was just given up here, which is that I can equate x into sort of its momentum space operator equivalent. So if I do that, this is going to give me, let's move this down slightly. This is going to give me 1 over 2 pi h bar integral from negative infinity to infinity. This term is just going to get copied over, so I'm just going to copy paste it. And then x is going to become, so this negative I h bar I'm going to leave at the front here. So negative I h bar And then we have a d by dp, so I'm going to just pull that into this integral. That's going to give me, I'm going to write this in red, integral from negative infinity to infinity of d by dp of e to the I px divided by h bar multiplied by, and remember, so this x is basically going into this integral, right? I'm allowed to do that because this integral is in terms of dp, right? This whole integral is in terms of dp. There's nothing stopping me from moving the x right next to the e. So because of that, the x is attached to the e, so that means this derivative is purely for e. It is not for the entire inner term. So, and then we have phi of p comma t on the outside like that. Do not operate the d by dp on the entire inner term, because specifically in order to do this relation, in order to convert x into its momentum equivalent, it has to be attached to the exp term. So we're going to close that. Close this by dx. And at this point, well, what do we do now, right? Because remember, our final goal is sort of to convert everything in terms into like sort of this dp integral. So right now we have three integrals. We have one dx and two dp's. How do we turn this into a single integral in terms of dp? Well, remember, the second part of our hint is to use equation 2.147, which is this equivalency of using Dirac delta. And the reason why we want to use it is because the Dirac delta has this very nice property that it can pull exact terms out of integrals. So if we can add some Dirac deltas into this expression by converting our complex exponential integrals into Dirac deltas, we can start getting rid of certain dp and dx terms. So how are we going to do that? Well, immediately I see that sort of this term, or this integral right here, is a derivative of a function in terms of p and a standard function in terms of p. Well, we can sort of change this via u sub, right? We can switch them around using u sub, because it looks like sort of the final goal is to get everything in terms of sort of just an infinite integral of e to the ikx. Well, right now I have a derivative of that, but I want the normal term without the derivative. So one thing I can do is I can use u sub and switch this derivative onto the phi side instead. So let's do that, right? Suppose that I set u to equal phi, and I set dv to equal d by dp of e to the I px divided by h bar dx. So in that case, well, v is going, sorry, not dx, dp. Okay, so in that case, v itself is just going to equal e to the I px divided by h bar, and du is going to equal d phi by dp. Or I suppose because of the fact that phi is in terms of sort of two variables, p and t, is going to be a partial with respect to p of phi. And then we'll close it with the dp like that, right? So in that case, our integral right here is going to equal, so this integral is going to go down and equal uv phi times e to the I px divided by h bar, evaluated from negative infinity to infinity, minus the integral of v du with the same bounds, negative infinity to infinity. So v du, that's going to be e to the I px divided by h bar times the partial with respect to p of phi dp. And I'm going to close it like this. So remember that for any wave function to be valid, it has to be finite and normalizable, and fundamentally the requirement for something to be finite and normalizable is that it has to go to 0 at infinitely far away. So automatically we just assume that this goes to 0. So in which case this is going to give us negative integral negative infinity to infinity e to the I px divided by h bar d by dp phi dp. And at this point, if I shove this back in here, well, the negative in front of this negative I h bar and the negative here will cancel out, so that's going to make a positive. So my expectation value of x is going to ultimately equal 1 over 2 pi h bar times the same stuff at the front. I haven't changed the front. I'm going to get rid of the negative at the front here, and then multiplied by my integral from negative infinity to infinity of e to the power of ipx divided by h bar times d by dp of phi multiplied by dp, and I close this all out with my dx term, like that. Okay, so at this point, we're at sort of a bit of a mathematical impasse, because it seems like sort of we can't really progress any further from this point. Because what does this look like, right? This is a triple integral. It's in terms of dp, it's in terms of dp again, and it's in terms of dx. We're trying to equate this, as per the instructions, into a single integral in terms of only dp. Well, we have multiple avenues to explore, so let's see what happens when we do each one. First option, just combine everything into a single triple integral and hope for the best. And immediately you should see that that won't give you the answer you want, because what's going to happen is that, you know, this thing, this e to the ipx term, is going to take the complex conjugate, become a negative, is going to cancel with this, and you're going to lose two complex exponentials. All of a sudden, you're now stuck with a triple integral that doesn't have any complex exponentials, and you can't take advantage of a Dirac delta. So that's sort of a dead end. We can't do that. Alternatively, maybe we can use the Dirac deltas, maybe we can use the complex exponentials as is and equate them to Dirac deltas. Well, you have a complex exponential, but you have this extra factor phi, p comma t here. So, you know, that won't let you do any conversions. You have same thing here, right? This extra factor, d by dp of phi. That's not going to let you do this conversion. So, once again, we're stuck. And at this point, it's like, okay, what do we do next? Well, one unusual aspect of this problem is that, you know, notice that it's a triple integral, but two of your three integrals are of the same variable dp, right? That's not typical of most mathematical problems. When you have something like that, it typically means that something's wrong. Or not necessarily that something's wrong, but that you're going to end up losing terms or like unintentionally canceling variables, because in actuality, right, these two p's are going to interplay with each other in the actual math. But the problem is, because of the fact that these two integrals are sharing the exact same variable, you have a case like this where you're getting unintentional cancellation between complex exponentials, which actually have very useful mathematical expressions to them that can sort of massage your expression into something that's more easy to handle. So whenever you have a situation like this where you're dealing with multiple integrals and some of them just are using the same variable for whatever reason, one thing you can do to sort of avoid losing possibly useful mathematical terms is you can just arbitrarily enforce that these same variables are actually become different variables. And what I mean by that is that what I can do is I can say, okay, I'm going to just reassign all of the p variables in this integral into p primes. And we're going to keep all the p variables in here as standard p's. And what that's going to do, well, you can just look and see what happens. So 1 over 2 pi h bar stays the same. I have a triple integral, like this. And then I have e, and now I'm going to actually take the complex conjugate. So e to the negative I p prime x divided by h bar times phi star of p prime comma t. And then I have my I h bar term. And then I have e to the power of I normal p x divided by h bar times partial with respect to p of phi of standard p comma t. And I'm closing this dx dp prime dp, like that. And now, all of a sudden, right, you have a way to combine these two exponentials without them canceling and causing you to sort of lose their mathematical usefulness. So now I can combine them, and I get 1 over 2 pi h bar, the same triple integral, but now e to the I p minus p prime x divided by h bar And then we have the same thing as before, phi star p prime comma t I h bar e to the power of, or sorry, that disappeared already, d by dp of phi of p comma t dx dp dp prime. So now notice that you have just a single term that is in terms of x, which sort of implies that we can start getting rid of the dx terms by converting into a Dirac delta, right? So we have some options here at this point, because we have something that can get turned into a Dirac delta, and we have three possible variables we can play around with. So the question now is, are we going to turn our Dirac, or are we going to create our Dirac delta using a dx term, or are we going to create it using a dp term, right? Because this Dirac delta expression, we can repurpose it into, Dirac delta of k is equal to 1 over 2 pi times the integral from negative infinity to infinity of e to the ikx, but this time in terms of dx instead. And that this is equivalently the same thing. It's just I'm switching the variables around, equating x with k instead. But in this case, your k would be whatever the p term is. In this case, your k is p minus p prime over h bar. So the question now is, are we going to get rid of the dx integral by converting the dx integral into something in terms of Dirac delta of x? Or are we going to do it with dk? Or in this case, I suppose dp, right? So look at this, negative infinity to infinity, e to the I p minus p prime, x divided by h bar. And let's try it with dx. So in this case, I am looking at this, right? This is going to give me 2 pi times the Dirac delta of the k equivalent term, which in this case is p minus p prime divided by h bar. So if I do that, then this is going to equivalent to 1 over 2 pi h bar, integral from negative infinity to infinity, integral from negative infinity to infinity. It's just a double now, right? And this is going to become 2 pi times the Dirac delta of p minus p prime divided by h bar, multiplied by phi star of p prime comma t times I h bar times the partial with respect to p of phi comma p comma t, and then now just dp dp prime. And at this point, okay, well, now we can start taking advantage of the Dirac delta, right? But before we even do that, think back to problem 2.23 and recognize that you can just literally pull the denominator, which is a constant, out as a product, right? Dirac delta of p minus p prime divided by h bar is just equal to h bar Dirac delta p minus p prime, right? So in that case, you can pull the h bar out in front of the 2 pi h bar, in which case that cancels out completely with the front term here. So this is going to give you negative infinity to infinity, negative infinity to infinity, Dirac delta p minus p prime, phi star p prime, comma t, I h bar, partial with respect to p, phi p comma t, dp dp prime. And now we can just turn this back into something purely in terms of dp by pulling out p equals p prime, right, of one of these integrals. So this is going to turn into a single integral where p is just equal to p prime. So phi star p comma t times I h bar times d by dp phi of p comma t dp. And just like that, we have our answer, right? The position operator in momentum space evidently is equal to I h bar d by dp. And with that, we're sort of done with this problem. Now, this problem initially says that in principle, you can do all calculations that we've done so far in momentum space just as well, though not as easily as in position space. So remember that at the beginning, I sort of made the point that you really have to be careful when you do sort of this illegal substitution of a Dirac delta, because it provides sort of certain assumptions. If you're not entirely sure of what I mean, go back to 3.12, where that was where we sort of checked if those assumptions were valid for a similar system in which we actually had to solve a problem. And what this is claiming is that you can always use this equivalent method. And since we obtained this method using this illegal Dirac delta transformation, what this implies is that actually, in fact, whenever you do sort of a momentum space problem, right, or whenever you want to switch to momentum space, you can always do it, even though this is technically an illegal move, right? You can sort of the implied physical constraints you pose onto any given problem by doing this Dirac delta equivalency, it turns out that they will always be physically valid no matter what. So that's just, I just think it's a very cool thing, which is that, even though sort of this is something that you have to be very careful when you do, in terms of strictly switching between momentum and position space, just doing it for any general physically realizable system is allowed, and it turns out that any constraints you apply onto sort of your physical system in order to do this conversion, none of them will make your system physically not realizable. And with that, we are done with 3.13 along with this chapter. So, or not this chapter, but this section. So I believe next is going to be the uncertainty principle, but visited in terms of linear algebra. So I will see you on those videos.